In this video, I'd like to introduce the idea of a geometric series. And before we talk about what a series is, let's remind ourselves what a geometric sequence is. So it's a pattern of numbers that has what we call a common ratio. So to go from one term to the next, we are going to be multiplying by the same number. So in this case, for this particular sequence, every step of the way, we are just multiplying by 1/2, or we're dividing by 2. And this number we call the common ratio. So a sequence is essentially the pattern, and usually these go on forever. Now, a series is when we add up every term in the sequence. So if I make just a bit more room here, the geometric series is, like I mentioned, we're just going to add all of these terms in the pattern. So 8 plus 4 plus 2 plus 1 plus 1/2, and so on. These are infinitely long, so we're going to be adding up an infinite amount of numbers, and in many cases, this actually does sum to some finite value. Now, there are many geometric sequences that don't. But this one in particular actually adds up to a number. In fact, it's going to add up to 16. And in a later video, we'll talk about how you can actually demonstrate this, how you can actually add up an infinite amount of these terms. But like I mentioned, for some of these series, like let's say 1 plus 2 plus 4 plus 8 plus 16 and so on, this is not actually going to add up to a number. In fact, if you just start adding term by term, it's just going to get bigger and bigger since the terms that you're adding themselves are getting bigger and bigger. So this, we would say, diverges, or it approaches infinity as the terms increase. Whereas this series right here, we can say this converges. It actually adds up to a specific number. And with these series, we actually use a completely different notation. We use what is known as the summation notation, and we're going to use the Greek letter for sigma, or it's essentially their capital S, so sigma in the Greek alphabet. And this just stands for sum, or summation. And remember, sum just means adding. And to use this notation, we want to first remember what the explicit formula for a geometric series is. So let me write that down. So when you have these sequences, the explicit formula for finding a term in this sequence, we can say that this sequence is called f of n. To find the nth term in the sequence, you take the first term and you multiply by the common ratio, which we'll just call r, raised to the n minus 1 power. So for instance, as an example, if we put in f of 4, we know the fourth term is going to be 1, but let's just prove to ourselves that this works. So the first term is 8, that's f of 1, and we're multiplying by that common ratio 1/2 to the 4 minus 1 power, or 1/2 to the third power. And 1/2 to the third is 1/8. 8 times 1/8, that is 1. So it does make sense compared to what our sequence actually is. Now, essentially, we're going to apply this explicit formula, which we can again write more generally. So for our particular case, we have that f of n is the first term, which is 8, multiplied by the common ratio raised to the n minus 1 power. So we want to sum every term in this sequence, and we can use the formula to do so. And we're essentially, for this one, starting with a term value of 1, or a term number of 1. So in our summation notation, we put n equals 1, that's our starting value, and we're going to add up all infinity of these. So we're just going to assume that the term number is going to go on forever, and we'll put our explicit formula in here. So this will be 8 multiplied by 1/2 to the n minus 1. And like I mentioned, this is just going to be equal to 16. So this is the notation we're going to use. It's cumbersome and a little bit difficult to learn at first, but it does compactly write this infinite sum we have here. So it's useful. And it's not too bad to use. You just need to get used to writing out one term at a time. So for instance, when n equals 1, you just plug 1 in here. You get 1/2 to the 0 power, which is just 1. And so that first term is 8. And again, this sigma, this Greek letter here, this capital sigma, just stands for sum. So every time you increase the n value by 1, we're going to put a plus sign because we're going to add up all those terms. So this is for n equals 1. Actually, let me make this a little bit more clear. So now we can plug in for n equals 2. When you do that, you get 2 minus 1 up here, or just the first power, and 8 times 1/2 is just 4. For n equals 3, again, we're just putting a plus sign between each of these terms here. For n equals 3, we get 3 minus 1, so 1/2 squared, which is a fourth. 8 times a fourth is 2, and we already found when we plug in 4, that's just 1, and so on. So the notation takes a while to get used to, but it, like I mentioned, does compactly write these series. So in a later video, we're going to talk about how you actually add these up, and we're going to look at specific examples. And then eventually, we're going to come up with a formula for a very generic series or geometric series where you have some starting value, and then we're going to multiply that starting value by the common ratio. So if we want to look at the sequence first, it would be a, then AR, then AR squared. Since every step of the way, remember, we're just multiplying by R. So the third one, we do it again. Now we have 3 R's multiplied, then 4, and so on. So we'll look at what happens when you actually add up every term in this series, or every term in this sequence. So the series is when we actually add it all up. The sequence is just the pattern. So it'd be A plus AR plus AR squared plus AR to the third, and so on. And there's actually a formula where this is equal to something depending on what the R value is. Because if you're multiplying by a number bigger than 1 or even equal to 1, it can cause problems. It can cause the series to add up to an infinitely high value, or we would say it would diverge. But if R is a fraction, negative or positive, then you can usually add these up.